general relativity step by step. Now last time I was looking at how to have contravariant differentiation with respect to a superscript, a vector with superscripts and subscripts. The superscript has a plus correction for the changing of the coordinate bases, and the subscript has got a minus. So what I'm going to do now is I'm going to consider a vector with two superscripts as a matrix, I guess, or a second order tensor, covariant derivative with respect to k. So in order to figure out what that thing is, I'm going to consider a contraction of it, Tij ui, let's say Vj, summed over I and j, of course, covariant differentiation with respect to index k, equals di by di x k of Tij ui Vj, which equals di Tij by di x k ui Vj. So I'm differentiating each term in turn. Tij times di ui di x k Vj. See again how I'm casually maintaining the summation convention from here, which is summed over I and j here, and it just works. It's a piece of magic that. Even now, I think to myself, wait a minute, it's summed over I and j, doesn't matter. Tij, what have we got next? Ui, di Vj by di x, superscript k. Okay, well that's great, but it's also equal to the covariant derivative commutes past multiplication, so not commutes past, but we can use the product rule. So it's Tij semicolon k ui Vj plus Tij ui semicolon k plus t. No, I'm getting out of step here. Tuv, tuv, and the index on v was j, plus Tij ui Vj semicolon k. And these two things are equal. So we can equate them. We can equate them, and this is the thing we want. We want this. We want this. But we also know that because we're differentiating covariant differentiation with respect to a subscript, I'll just do one term here. So this guy here is equal to di ui by di x k, and because it's a subscript it's minus u. We're going to contract over L, let's say, and what have we got left? We've got an I and a k down there. Is that right? Yeah, that's right. Now the upshot of all of this is that after you account for everything, we want this. We're going to get the same thing as last time, except that these are arbitrary. And I'm going to get some long complicated expression, ui Vj equals 0 for arbitrary ui and Vj, so the thing in the brackets must be 0 as well. So we just go through that process and do it, and what we get, is that Tij semicolon k equals di Tij by di x k plus, I'm going to write the lambdas in, I'm going to write my t's in, ij plus, I'm going to write my gammas in, that's got, oh no, I'll put ij there and we're going to contract over those indices. I'll just leave those as dots and I'll put them in a minute. So we've got 1 upstairs and 2 downstairs. Here T has got 2 upstairs. What we do is we take each index in turn. Well, you can see what's happening here because what we've got is the covariant terms here, j. And so we're effectively contracting on the second index and the first index as well. So let's see if I can get this right. We've got ijk Yeah, okay, we've got an I and a J. Okay. We're going to contract on each index separately. So we've got an L here, which is going to contract with an L down there. And here we've got the second index L, which is going to contract with an L down there. Now, we have got K on the bottom. That's the only index that's free on the bottom. That must be there and there. And now, I've got I and J and J and I. Oh, yeah, summed over L, of course, summed over L on both terms on the left and the right there. So what have I got here? We've got I and J on the top. We've got here is represented, or it's representative, I guess, on the right is in the Christoffel symbol, and here the index I is represented on the tensor T itself. J is once on the index itself here, and once here on the Christoffel symbol. You'll notice the sign of the correction, which is a plus in both cases, because we've got two superscripts. Yeah, I'm going to stop there. Nice little formula, that.